It is now 1 o'clock Eastern, and because we have a lot of ground to cover, we are going to get things started. Once again, hello and welcome to the October edition of the Insights and Innovations webinar series hosted by the International District Energy Association. My name is Scott Zeitcher, and I serve as membership manager for the association. Today's webinar is titled Large Heat Pumps, Carbon Reduction with Great Economics, presented by Johnson Controls Incorporated. Before we get to the specifics of the presentation, I'd like to go over just a few housekeeping notes. This webinar is scheduled for 1 hour, including the presentation, and approximately 15 minutes for Q&A, although we can run as late as 2:20 Eastern Time if we receive enough questions from the audience. This webinar will be recorded and streamed on the IDEA website within 24 hours of its conclusion. Registrants will also be sent a follow-up email with links to the recording and presentation slides. A link to the presentation slides is also provided in the chat box if you want to print out and follow along. Please submit your questions via the Q&A box during the presentation portion of the webinar. The Q&A icon can be found in the menu bar at the bottom of your screen. Questions will be reviewed by IDEA and posed to the presenters by the host at the conclusion of their presentation. Finally, if you're having audio or video issues, please send a note in the chat function to our host, Jason Beal. As mentioned previously, today's webinar will discuss the application of water-to-water heat pumps. Our presenters will demonstrate how heat pumps can be phased into your existing facilities and how you can achieve the greatest ROI. Two of the biggest fundamental questions our presenters will review and answer are: how can you achieve 3 to 4 times the efficiency of a boiler? And what heat source will make the most sense for you when you shift away from fossil fuels? Our goal is to help central plant owners and operators and energy service companies understand the hidden benefits of utilizing water-to-water heat pumps to assist in the short and long-term decarbonization goals while best managing your capital expenses and optimizing your operational costs. To discuss this problem, we're pleased to be joined today by 3 executives from Johnson Controls, a global leader in building efficiency and district energy solutions. Rajesh Dixit is a chemical engineer and an MBA with nearly 30 years of global experience in industrial chiller and heat pump technologies. He is the Director of Global Product Management for Johnson Controls Building Technology and Solutions Divisions based in York, Pennsylvania. He is an active community volunteer, an ex-chair of the ASHRAE TC 8.3 committee, and a board member of the Belmont Theater in York, Pennsylvania. We're also joined by Kit Franson, the Director of Equipment Sales Programs for Johnson Controls. Kit has spent his entire 11-year career in a variety of product management, sales, and engineering roles at several HVAC&R manufacturers, where he developed, supported, and promoted solutions for high-performance buildings. He is passionate about green building design and educating the industry on the latest innovative technologies and systems, and he is responsible for strategic initiatives and sales enablement for Johnson Controls equipment business. Kit earned a Bachelor of Science degree in Aeronautical and Astronautical Engineering from Purdue University. Last but not least, we're joined by Jonathan McCrea, Johnson Controls HVAC Equipment Sales Manager. John has spent his 26-year career in a variety of HVAC sales and leadership roles with Johnson Controls, helping its teams deliver high-performance equipment and control systems for their customers. He is a passionate proponent of decarbonization and helping building owners achieve operating cost savings through innovative, energy-efficient solutions, and he earned a Bachelor of Science degree in Industrial Engineering from Georgia Tech University. So without further ado, we'll turn things over to the presenters. Take it away, Rajesh, Kit, and John.
Thanks, Scott. Hi, everyone. Once again, I want to thank you for joining this webinar. We'll be reviewing one of the most practical ways to help decarbonize larger heating systems with heat pumps. I'm excited for this discussion today because of 2 reasons. One, the stars are aligning where investing in heat pumps has a very meaningful impact on financial returns. And secondly, the industry is more innovative than ever, leading to almost an easy button for converting traditional chiller and boiler systems to hybrid or even fully electrified heat pump systems. All right, so let's get into the agenda today. So first, we'll start by going through key objectives and get you thinking about what it means to set your path to decarbonization. From there, we'll review the why on decarbonization, as well as electrification in today's environment, and what's motivating building owners to look at large heat pumps as a solution in the short and long term. In the back half of the presentation, we'll get a bit more technical and review the basics of heat pumps, discuss advantages over traditional cooling and heating, outline some modes of operation of this equipment, and cover a very common heat pump system configuration. Lastly, we'll give you some guidance on how to best evaluate a new or existing system for large heat pumps and share an example project showing you what kind of sustainability impacts and operational savings you may see with your project over traditional cooling and heating. So what does it mean to decarbonize, and where do we begin? Well, I can tell you there are almost limitless combinations of building system components that can optimize and reduce carbon emissions. And there's not a one-size-fits-all approach. And as you would imagine, it would depend on a variety of different factors, such as whether the project is greenfield or existing, where the project is located, how the building or set of buildings is to be used and operated, and what equipment or power to generate that equipment is available. The more common technologies discussed as of late have been renewables, green fuels such as biofuels or hydrogen, carbon capture, renewables such as on-site solar or wind, electric boilers, and of course, heat pumps. But in the middle of all of this is thermal storage, and either through tanks, batteries, or the earth. And we should be looking at how to reuse as much energy as possible that is available, which allows us to reduce risk and maximize efficiency of these systems. Either way, all of these components mentioned must be sized and controlled optimally, like a choreographed dancers in a ballet as an example, in order to see that full benefit. But before we start to solution your goal of decarbonizing, you need to think about what is driving this need in your project, either from internal or external factors, what the end goal is, and how to make it achievable through electrification or other means. Every organization is different, right? And many look at long payback periods as acceptable due to the wider impact on society and the environment. I would say decarbonization is almost like running a marathon, right? You need to prepare, set realistic goals and milestones, and train over a period of time before you can run 26.2 miles. This is why phased-in approaches often make sense for decarbonizing the project, not trying to get there all at once, and lead to better returns in both sustainability and finances. Large heat pumps can be that first phase for you, as they are practical and can be applied in a wide variety of applications. So where are you at in your quest to decarbonization? Let's start with a quick poll today. So as this poll gets pulled up here, no pun intended, which of these most closely resembles your and/or your client's sustainability targets? So you can choose one or many of these selections here. So we'll give you about 30 to 40 seconds here to select your choice. We need some Jeopardy music in the background. I think that would be fun to add the next time. All right. I am not seeing the results at this point, Jason. Oh, something happened here. All right, it just got pulled up on my screen. So it looks like the number one response here, about 56% was emissions reduction target by 2030. So science-based target. Wow, interesting. And then we got a close second here being energy efficiency or intensity target, which that's kind of I was thinking was going to be the most common response there. So great input from everyone. Really appreciate it. And so we'll close the poll out here and move on to the presentation, the rest of it here. So once again, I appreciate everyone's participation on that poll and had some interesting results there. But moving on now, how did we get here in today's environment with decarbonization? So let's start by going through some macro drivers and trends. Ever since the oil crisis in the 1970s, there's been standards such as ASHRAE 90.1, along with regulatory measures introduced to increase building system efficiency. Then came along the Montreal Protocol, Kyoto Protocol, and more recently, the Kigali Agreement, meant to focus on reducing overall carbon emissions either directly or indirectly via the use of low GWP refrigerants or other means to help reduce climate change. Essentially, these treaties have made governments around the world commit to net zero greenhouse gas emissions. An example of this is in the image on the left, which shows the USA's net zero greenhouse gas emission goals over time here. So as a product of these goals and the desire to reduce greenhouse gas emissions, many governing bodies have created a path for building owners to work to net zero emissions, with most of it being driven by codes and standards or regulations. Essentially, the first step is to further increase efficiency of buildings, inclusive of weatherization as an example, then electrify heating sources to reduce carbon emissions, and then from there look to offset building carbon emissions and then use on-site renewables to achieve net zero. So that would be basically kind of that path to get there. In addition to the commitments by our governments, many corporations are now adopting ESGs, or environmental, social, and corporate governance, to demonstrate the non-financial performance indicators to ensure accountability and that they are adequately managing the carbon footprint. This sounds great that we have these goals and commitments, but why has there been so much urgency on decarbonization as of late? Maybe asking that question. Well, this topic has become more urgent than ever, with the accelerant being global inflation and the war between Ukraine and Russia, which has led to many new regulations forcing the change of converting the way we've traditionally heated and cooled spaces to more sustainable and resilient type solutions to hedge against deglobalization. You can see this in multiple states and municipalities, and so you can see on the right-hand side there that graphic where you've got California, Washington State, Washington D.C., or even New York, introducing natural gas hookup bans or setting policies going above and beyond federal regulations around efficiency. Many think these regulations are only applicable to new construction projects. However, there are now regulations being put in place, such as building performance standards, or BPS for short, to address this in existing buildings. So it's coming fast, and not doing anything is no longer an option. So what else is accelerating decarbonization? And I would say it's costs, right? So a few years ago, based on the project scope or location, it may not have made sense to invest in or apply technologies to decarbonize due to traditional systems having better payback periods. Well, all that's changed now in the past year, where across the world, fossil fuel prices are rising at almost a parabolic rate, leading to situations where facilities must curtail usage or even shut down due to the financial burden. In conjunction with that, you've got carbon taxes, which really started in Europe at first, are either in place or being evaluated in North America as a tool combined with regulatory measures to drive building owners to decarbonize. So furthermore, what you may not realize in all of this is that even if natural gas rates come back down, heat pumps have always had an attractive payback in the 5 to 7 year range. But as we'll discuss later on in this presentation, and even in the second series as well, you'll see that there are even shorter timeframes now from a payback perspective. So that in mind, why deal with the volatility of fossil fuels when electricity production can come from a variety of sources and still get you down that path to decarbonization? So after looking at these drivers, what is happening to the design of cooling and heating systems? Well, there are a few things. First, as mentioned before, either through codes and standards or increased energy prices, equipment is needing to become more efficient. HVAC and building systems are seeing new technologies and control strategies, leading to significant improvements in how they operate and maintain thermal comfort in spaces. I look at smart digital solutions, such as like digital twins, as a game changer in the HVAC industry, leading to buildings operating as intended and able for owners and operators to better connect to their building systems. Secondly, embodied carbon is now playing a role in the building design process, which is different than the operational carbon that most people are used to in terms of operating your equipment, and you get those direct and indirect emissions. So what is embodied carbon, you may ask? Well, embodied carbon consists of all the greenhouse gas emissions associated with extracting, transporting, manufacturing, and installing building materials or equipment on site, as well as the operational and end-of-life emissions associated with them. Eventually, embodied carbon will be used as a mechanism to attack the upstream carbon emissions and forcing building owners to choose manufacturers who are diligent about using as little carbon as possible in producing their products. Lastly, you will see electrified heating become the norm. And that will be mainly driven by heat pumps, both direct expansion and hydronic, which we'll cover at length today, along with technologies that enable us to store and reuse energy in buildings. On top of this, the equipment that you are normally accustomed to using today may change in how it's controlled. An example of this could be no longer applying airside economizers, so you can leverage heat sources for your heat pump systems. And we'll talk about that more a little bit later. So as these changes are happening to the design of our cooling and heating systems, which is leading us to greener pastures, we've got a big elephant in the room to deal with, and that's existing buildings. So many existing buildings have hot water systems that use boilers that produce up to 180 F hot water, and converting those systems to lower temperature type systems, which is typically produced by many water heat pumps today, can be costly and add significant length to a project timeline. So as an example, let's say you've got a heating coil or heating coils rated for 180 F. Now you're expecting the same coils to deliver the same BTUs or heat at 120 F from a water-to-water heat pump. More than likely, you'll have to install a larger coil or set of coils or increase your flow rate in order to meet the thermal comfort requirements. So the good news, though, in all of this is that innovation is here as manufacturers and building designers are now teaming up to develop unique and realistic systems with large heat pumps to meet this higher hot water requirement. So electrification and heat pumps sound great, but what about our electrical grid to support this? I always get that question. And did you know that some power is cleaner than others, right? So in the chart on the left, what you'll see here, this comes from the EPA, that the grid cleanliness in terms of carbon emissions is very regionalized. Out west, many utility providers can leverage natural resources such as hydro and wind to be able to power buildings. However, many other areas of the country may use fuel sources which can be either dirtier than natural gas, for what you're using to power your boiler. So it's important to do an upstream carbon emissions analysis and remember that over time, the grid will become cleaner as more renewables come online through investments made by the governments or utility providers. So even if your power supply is not green today, consider the fact that since 2014, renewables used for power generation in the US has increased substantially, and that's not slowing down. But with all this being said, there's not an unlimited supply of electricity available, and that's why it's important to digitize your building and manage electrical demand, as well as have contingency plans in place for being able to continue to operate your building's heating and cooling systems. So contingency plans, they may include having a phased-in approach to full electrification as the grid becomes cleaner and more stable, using backup boilers, and or using thermal storage as part of your design to handle, to do some peak load shaping. So just to summarize our first section here, every organization is different. And there will always be varying priorities. You'll have some organizations purely driven by sustainability, either through ownership or investors. You'll have some organizations financially motivated by seeing their utility bills skyrocket and looking for alternative solutions to lower their operating costs, which you'll see more on the right side there. And then you'll have some organizations that are just in the middle, just trying to be forward-looking and reducing their impact on the environment while saving some money in the process. Either way, many regulations will be driven by carbon emissions or even water reduction goals to help keep our planet and our future intact. However, what most people don't realize, though, is that even if they aren't impacted by rising utility costs, this could end up really hitting their wallets as fines or additional taxes may come along if they don't comply. So local law 97, New York City is a perfect example of this, and hence why it's important not to brush off these legislative measures and truly understand the overall impact. So yes, environmental and sustainability commitments, along with economic factors, are the macro factors driving owners to look at large heat pumps. But why heat pumps specifically? Why this technology? So let's talk about this on the next slide. And it really starts with how effective heat pumps are at moving energy or moving heat. So as a reminder, coefficient of performance, if you're not an engineer, or COP, is power output over power input. Boilers and electric resistance heaters are limited to COPs under 1 because they're creating new heat, while heat pumps can achieve far greater efficiency since they're moving heat from a heat source to a heat sink. So to give you a simple example representative of like your home air conditioning as an example, heat pumps, what they do is they actually extract energy from the outdoors, add heat from electricity, or called the heat of compression, and move this energy and then deliver it to the space. So in heating only systems or applications, which is representative of the example I just described, large water-to-water heat pumps can easily achieve COPs of 3 or higher. At today's utility rates, operation of these systems is generally less costly than burning fossil fuels. So where things can get really exciting, though, from an economic perspective, is when large water-to-water heat pumps are applied, leveraging a chilled water load and a primary heat source. So basically, both cooling and heating at the same time. While operating in this configuration, COPs are over 5, and you can see from down at the image down below on the bottom half of it, it's about 4 times the amount of conventional cooling and heating from a COP perspective. So once again, heat pumps only move BTUs or energy, so they need to have a heat source that has enough energy to support the heat sink. So when these two are not balanced, or the heat pump is not sized properly, the heat pump will not operate as intended, and many, in fact, will even shut down or even cycle. If you don't have the ability to extract enough energy, or if you have too much energy, as an example too, that can happen, and you can't appropriately reject it, so the equipment needs to shut down. So you can see, though, in this list on the left-hand side, there are many sources which a heat pump can extract heat from, and the available heat can be used for many purposes, from direct space heating to reheat, domestic hot water, process heating, as an example. So once again, any installation where you've got an adequate source and a sink and they coexist together may be a valid application for a heat pump. And I will just say, lastly here, the lowest hanging fruit, though, is leveraging the return chilled water and using that for heating hot water. So with that, I'm going to go ahead and pass this off to Rajesh here to talk a little bit more about this scenario. Hey, Rajesh, how's it going?
Good. Thanks very much, Kit. So how does a water-to-water heat pump provide simultaneous chill water and hot water, such as 42 Fahrenheit and 170 F, or 6 Celsius and 77 Celsius? So as many of you know, typical air conditioning chillers are designed within the limits of the available compression ratio of the compressor. These limits are quickly exceeded by the unique differential pressures encountered in high-head applications. These compressor design challenges are overcome by using the principle of compounding. A compound design arranges 2 individual compressors in series, the low-stage compressor and the high-stage compressor. By flowing the refrigerant gas through these 2 compressors in series, the pressure ratio becomes the sum of the 2 individual centrifugal compression ratios. So the result is a much higher total lift pressure available to the system, which can handle the high head demanded by the simultaneous mode. So Kit, let's go ahead and play the animation, please. Thank you. So our evaporator is a shell and tube type. Chill water flows inside the tubes. This is our source, as Kit mentioned in his previous slide. Uniform distribution of suitable refrigerant takes place over the entire set of tubes, as you can see in the animation, due to which the unit produces chill water, which is used for beneficial cooling. Mesh eliminators or baffles prevent the liquid refrigerant carryover into the compressor. The refrigerant gas leaves the evaporator section and passes through the low stage compressor onto the high stage compressor and finally into the condenser. The condenser is also of shell and tube type design, wherein the hot water is flowing inside the condenser tubes. This is our sink. The gas baffles distribute the refrigerant gas over the entire set of the condenser tubes, due to which the unit produces hot water, which is also used for beneficial heating. The heating capacity that we get out of the condenser is equal to the heat removed in the evaporator plus the compressor work that was done. The economizer that you see in this animation helps to improve the overall cycle efficiency. In the simultaneous cooling and heating mode, the control is based on the leaving hot water temperature, but can switch to the leaving chill water temperature if need be. Besides the the diversity of refrigerants that you see on this slide, it is also important to have design flexibility to handle large variations in flow rates and temperatures between the summer and the winter conditions. It is also important to have a very good turn down for the unit, turn down based on the design heating load. A typical operating condition is listed over here. Every condition is very unique. You can see the unit is producing simultaneous 42F and 170F, which truly helps, as Kit mentioned in his previous section, to have those conversions from the legacy steam-based system to hot water using the heat pumps. To summarize, below the animation, there's a simple schematic, but quite powerful. For every 1 unit of heat that is removed from the evaporator, 0.48 units of input energy is required to drive the compressors. Therefore, the 1 plus 0.48 is equal to 1.48 units of heat is available from the condenser. Thus, the combined COP becomes 5, which is almost 4 times higher than a conventional standalone chiller and a standalone boiler system. Basically, one equipment does it all, smartly moving the BTUs around rather than creating them. So this is a good representation of simultaneous cooling and heating mode. In this particular example, we have a cooling load of 1,800 tons, and we have done our best to include the metric units as well. 1,800 tons or 6 megawatt of cooling load from a hospital. So this is our evaporator source. We also have a coincidental heating load of 31,500 MBH or 31 million BTUs, approximately 9 megawatts of heating capacity that exists from academic buildings, labs, dorms, college campus. So this is our sink. So due to the principle of compounding explained in the previous animation, the unit is delivering simultaneous 42F or 6 degrees Celsius chill water for meeting that hospital's cooling load and 170F or 77 Celsius for taking care of the heating load. Such systems can also be extended and have been successfully deployed, I should say, wherever coincidental cooling and heating loads exist, such as in hospitals, airports, district heating, and industrial processes. So this is an idea webinar. It would be appropriate to quote a couple of examples that are of large capacity. So these 2 examples are great examples of low carbon, large capacity heating with high temperature lift. The heat pump units can be piped in parallel, series counterflow configurations. There are many possibilities that exist depending upon each application. The systems often or may involve a hot water storage tank, chill water storage tank, or a geo exchange field that adds wonderful flexibility to the overall system. This is something that we, myself, Kit, and John, the 3 speakers on this particular webinar, will be covering in detail in part 2 of our IDA webinar series coming up next month. But consistently between these 2 applications and many more that are not on this slide, the combined COP is 5, which once again is 4 times more efficient than a conventional way of cooling and heating. So in some cases, the heat pump should be capable of running in the cooling only mode, similar to a typical water-cooled centrifugal chiller. So as you can see from the animation that Kit is playing, in this particular mode, the high stage compressor is shut off. Only the low stage compressor is operating due to the low head conditions. This practice allows the chiller to run more efficiently and take advantage of the condenser water temperatures that are well below the design. In this particular mode, the control is based on the leaving chill water, and this mode is also sometimes referred to as the heat recovery chiller mode, in which case the condenser water can be used for some domestic heating purposes. Now we are going on to our last mode, which is the heating only mode. I won't explain this mode in detail because this mode is actually very similar to the simultaneous cooling and heating mode animation that we showed you previously. There is only one difference, which is in the evaporator section. Whatever is passing through the evaporator tube bundles is referred to as the low temperature heat source and not chill water. So it is something other than chill water. What can that something else be? It can be sewage wastewater, cooling tower water, can be coupled to a geo exchange field, river water, lake water, low grade industrial process water, or any sort of a low temperature waste heat. So the water that is cooled in the evaporator is simply returned to the source and is not used for beneficial cooling. Using the principle of compounding with two compressors operating in series, the heat pump overcomes the high head condition, delivering very high temperatures such as 170 degrees F or 77 Celsius, which is used for beneficial heating. The control is obviously based on the leaving hot water temperature. And in this particular example, the one listed on the bottom left of the slide, the source is actually city's wastewater at 43 F or 6 Celsius. And the sink is 154 F or 68 C, which is used for district heating of a large metro city. So to summarize the heating only mode, we are feeding one unit of some sort of a low temperature heat source in the evaporator and using 0.48 units of energy to do the compressor work. So the 1 plus 0.48 equal to 1.48 units of heat is what is available from the condenser. And therefore the heating COP is 3, which is 3 times more efficient than a fossil fuel fired boiler. So similar to our previous modes that we explained, let's discuss about 2 examples that are great examples of low carbon district heating. Once again, we are not producing any chill water for beneficial cooling. So we are feeding the evaporator with something that is other than chill water. The first example is in Western Europe, where the heat pumps are delivering as high as 185 F or 85 Celsius hot water for district heating. The evaporator source is river water, whose temperature fluctuates largely between summertime and wintertime. In summertime, it is about 73 F or 23 Celsius, and in winter, it drops down to 55 F or 13 Celsius. There are 2 compound-style heat pumps piped in series counterflow configuration, delivering 51 million BTUs of heat, which is approximately 15 megawatts, with a heating COP of 3. The second example is underway in Central Europe, involving 3 large, or I should say super large, high-head multi-stage centrifugal heat pumps, recovering the heat from the municipal sewage to deliver 199 degrees Fahrenheit, 199 degrees Fahrenheit, 93 Celsius for district heating. In this case, the heating capacity is 200 million BTUs, 200 million BTUs with a COP of almost 3 point, heating COP of almost 3.8. In both examples, you can see that the refrigerant is R1234ZE with a GWP of less than 1.0, GWP meaning global warming potential. We decided to include this particular slide, although the title of this, the focus of our today's discussion is around heat pumps and simultaneous cooling and heating. But this slide is for cooling only, but applying the benefits of the compounding technology in high head conditions. The first example is where water is an issue, meaning water is not available. So we have air-cooled condensers, or sometimes referred to as radiators, to cool the condenser water that is flowing through the units. Because it's air-cooled, the entering condenser water temperature to the unit is very elevated, such as 135 F or 57 Celsius, as you can see on the slide. Thanks to the compounding technology, the unit is able to deliver as low as 39 Fahrenheit or 4 Celsius, which is used for comfort cooling. The second example is of brine chilling, where the unit is producing as low as -1 Fahrenheit, -1 Fahrenheit or -18 Celsius for process cooling. Another thought that comes to mind is ice thermal storage that Kit mentioned as a decarb solution. So this compounding technology can also be used for producing ice for ice thermal storage tanks. That is something that we'll cover in part 2 of our webinar next month. So we covered 3 modes of operation. This is my last concluding slide in terms of modes of operation. So thank you for listening. I'm going to hand it over to John.
All right, thanks, Rajesh. All right, what we'd like to do now is to explain at a high level one of the most common and most economically attractive ways to apply a large water-to-water heat pump. This approach is sometimes called the sidecar configuration, and it's used in a system where there is a need for chilled water cooling and hot water heating year-round. So the heat pump, as you can see, is located where it can be connected to the chilled water and hot water return piping, which is commonly in a central plant where it's close to the chillers and boilers that are already existing. But it could be anywhere. It could just be in any place in your system where the heat pump can be connected to both of those loops. So as you can see, the system is operating with a 170-degree supply hot water temperature and a 20-degree delta T, and the chilled water is 56 to 42. And in this scenario, it's wintertime, so there's a relatively small cooling load in the system and a much larger heating load. So our heat pump has been sized to comfortably unload and handle all of the wintertime chilled water load in the system. So its pump is flowing all of the return chilled water through the heat pump's evaporator, and the heat pump's onboard controls are keeping the chilled water at a leaving temperature of 42 degrees desired by the system. On the hot water side, the heat pump's dedicated pump is flowing 150-degree return hot water through the heat pump's condenser, and it's producing approximately 170-degree hot water. And that water is then getting mixed in with the remainder of the return hot water and sent down the line to the boiler plant, where the boilers are taking it the remainder of the way up to the 170 that's needed in the system loop. And it's important to note that in this setup, our chilled water load is our heat source. And it's also the limiting factor in how much hot water we can produce with the heat pump. And we'll talk about this in our second session more coming up. But if you had a sufficient additional heat source and enough heat pump capacity, we could potentially handle all of the heating load and eliminate the need to run boilers at all. So if we look at that same system in summertime operation, what we have here is a lot of chilled water load and a relatively small amount of heating load. So our heat pump, again, having been carefully sized to comfortably unload and continue to run, handling the summertime minimum hot water load, it's receiving all of the system's 150-degree return hot water flow through its condenser, and then its onboard controls are delivering 170-degree supply hot water temperature that's required by the system. So the boilers are off and the heat pump is handling all of the heating needs in the system this time. And over on the chilled water side, our heat pump has plenty of heat source with the relatively high summertime chilled water load. And its dedicated pump is flowing a portion of the 56-degree return through the heat pump's evaporator. It's delivering around 42 degrees chilled water. That's then mixing with the rest of the return chilled water and then flows down to the main bank of chillers, where it's brought to 42 degrees, which is what we need in supply temp for the rest of the system. So in essence, we're extracting heat from the return chilled water. We're using the heat pump's compressors to raise the heat to a useful temperature through the refrigeration cycle in order to produce the hot water. And we're simultaneously reducing the number of cooling tons that the downstream chillers have to produce. So that's where we get this double effect where we're getting beneficial heating and cooling, and we can achieve the COPs that are 5.0 or higher. So obviously, depending on your gas and electric rates, this will vary, but you can really get some impressive operating cost savings as a result of this configuration. All right, so hopefully by now you're starting to see some really good potential for your organization with your systems. But the big question is, where do you start? What are some actions that you can take to move this forward and really take advantage of this technology? So I would say the very first thing you want to do is some simple qualifying to determine really whether your system is a good fit. And because it'll give you the highest COP and the best payback, what we really want to evaluate here is simultaneous heating and cooling a good fit for your system? Can we apply a heat pump in that fashion? So the first question is, of course, do your chillers and boilers operate simultaneously? And assuming the answer is yes, the next question is, does that happen some of the time or is it all of the time? And I would say in many cases for a campus loop or a district energy system, the answer is all of the time, a lot of times. So there's a base load of cooling in the winter and there's a base load of heating during the summer. So if you do have that situation in your system, you're very likely a great candidate for a large heat pump. So the next thing I would ask is, what temperature does your system require on the hot water side? And really what we're trying to answer here is your system able to operate with the temperatures that are currently available with today's heat pump technology? Just what can you tolerate on a winter design day and still satisfy the requirements of the spaces that your system serves? So you can't always use a hot water reset strategy, and we certainly encourage that during off-design conditions. But ideally, you really want your heat pump to be capable of producing the hot water temperature that's usable pretty much any day of the year. So let's assume that you have determined that you can live with 170 degrees supply hot water temp. The next step beyond that, and it's a really critical one, is to get a handle on what your loads are. So you're going to want to build a really good load profile. So the first thing that I would go to there is your building automation system. You want to make sure you have instrumentation in place and you're running trends that are going to give you a really good, clear picture of what your total system cooling tons are and what your total heating MVH is throughout the year. And once you've assembled that load information, at this point, I'd recommend engaging a heat pump manufacturer, either directly or in conjunction with your consulting engineer, and take a look at what sizing might make sense for the machine or machines that would fit with your system. And just in principle, you want to get the most benefit you can by maximizing all the heating that you can get from the heat pump, but it's very important to select it carefully. And as we've noted, consider the minimum heating and cooling loads when you're picking the heat pump. And generally what you want to do is ensure that the heat pump is able to run 24/7, 365 all year long, just without cycling off during its minimum load conditions. So that's a key part of it, because you want to maximize the amount of savings that you get from it. So, and by the way, you may find that the optimal configuration is 2 machines instead of 1. So I would say that's an important thing to look at just to evaluate. So heat pump manufacturers and many consulting firms can help you create a heat pump load model similar to the one on the right of the slide. And if you look at the green shaded area at the bottom, that represents the potential simultaneous heating and cooling savings opportunity. And then in the upper left, that reddish part, that's labeled supplemental heating. That's also an opportunity if you have a secondary heat source where you could use your heat pump capacity to handle the heating load and not have to use supplemental boilers. But we'll talk more about that in session 2. All right, so if we move on, beyond the loading graph, manufacturers, if you can move on to this next, manufacturers and consulting engineers often will have a first pass kind of high level heat pump analysis tool that'll help you get a good approximation of the net operating cost savings and also your sustainability benefits. So the heat pump analysis tool to the right has inputs for a lot of different things, but minimum and maximum cooling and heating loads, natural gas rates, electricity rates, and then a budgetary project cost as well. And it will spit out or give you a payback analysis with annual operating cost savings broken down into the different components, and then your CO2 emissions reductions as well as your water savings. So many times armed with this kind of preliminary analysis, you can begin to gain support for your project, getting the right people on board internal to your organization and helping them to understand the concept and the potential benefits, just so you can start the process of lining up funding for this significant project. Once you've demonstrated that you have an attractive opportunity, I would say the next step is to engage your consulting engineer and have them complete a more detailed system analysis with the heat pump manufacturer running a bunch of actual heat pump performance ratings. And then you're going to just use all that to really nail down the economics of the project in more detail. All right, so next I'd like to share with you an example here. And if we use this analysis tool, and this is just to give you a better idea of the magnitude of the savings that are possible here. So it's a hypothetical example, a large college campus with a base heating load in the summer of 19,000 MBH and a base cooling load in the winter of 1,000 tons. And based on that load profile, we've chosen a heat pump with 2,000 tons of cooling capacity and 38,000 MBH of heating capacity. And just some of the other assumptions, you can see we plugged in a 0.4 average kW per ton for the existing chillers, which are going to have to do less work now once the heat pump is installed. We have a power rate we've plugged in of 10.4 cents a kWh and a natural gas rate of $1.27 per therm. And these may or may not line up exactly, of course, with what kind of power rates and gas rates that you see. But the nice thing about these kind of simulations is it's very easy to adjust the utility rates. And it also will help you do a sensitivity analysis, as Kit alluded to. We don't know what's going to happen to energy costs in the future, and you can simulate that very easily. What happens if the natural gas costs continue to go up? What happens to the savings that I'm getting there? What if they go back to where they were originally, a year ago? You can simulate what your savings would be in either case. So as far as the savings projections go in this case, we have a natural gas savings of a whopping $4.8 million per year in that cost. We have an increase in electricity costs of 1.6 million because the heat pump is certainly going to draw more power. And then we have a water savings that's 30 million gallons per year because we're not sending anywhere near as many tons out to the cooling towers. So we have a lot less evaporation with that. And that adds up to 189,000 in additional cost savings. So the net cost reduction, once you consider all of that, comes to $3.4 million per year. And we have scope 1 CO2 emissions reduced of about 10,000 tons per year. So I will say, granted, this is something of an ideal case, and it's a very large machine with favorable utility rates. But it's not uncommon at all to see net savings well north of $1 million. And the paybacks that we're typically seeing, as we've noted, are under 3 years, especially with the natural gas rates where they are today. All right, so I think we're going to roll into a final polling question here. So thinking about your organization or your clients, depending on your situation, what we're asking here is, what would you say is the greater motivating factor that might cause you to invest in a large heat pump? Is it the sustainability, the decarbonization benefits, or is it more the economics, the operating cost savings that would drive it? So we'll give it about 30 seconds here. All right. Well, it looks like it's fairly close to even. I guess the economics are coming out ahead a little bit. And I would say that's been my experience talking to customers. I'm in the southeastern US, which might explain why I hear more about the economics and sustainability. Not that we don't care about it, but I think every company or every organization is going to have different goals, and the decarbonization commitments maybe a little further out. Economics could be driving it, so that makes sense to me. But all right, well, great. So to summarize, organizations across public and private sectors are increasingly setting aggressive decarbonization goals. And as we discussed, there are lots of ways that we can make progress towards these commitments, but there's a very short list of things that offer both substantial decarbonization and great economics. And so for district heating and cooling plants, college campuses, healthcare facilities, really any other system that requires both chilled water and hot water simultaneously, large water-to-water heat pumps are an excellent opportunity. So if your facility seems to be a good fit and you'd like to move forward, we'd highly encourage you to take some action, pull in some experts, and let us help you add a large heat pump to your system. You'll make great progress with your decarbonization and achieve one of the best ROIs of any HVAC investment out there. And with that, I'd like to thank all of you for your time and engagement, and we will go ahead and start the Q&A.
Thank you very much, John and Kit and Rajesh. That was very comprehensive and very informative. We have a lot of questions to get to. I will just say a few things about those, about the questions that we have received. Number one, we may not have time to get to some of the questions, but I want to assure you that those folks who have submitted questions, even if we don't get a chance to get to yours, the questions will be sent to the presenters, after the presentation, so they should be able to respond to you directly if we don't get to them during this webinar. Number two, sometimes questions will come in, and it turns out that 5 minutes later on a subsequent slide, one of the presenters tends to answer that question. I may still pose that question because my experience with webinars has been that some people have to drop off, a phone call comes in, life presents a lot of challenges. So in some cases, there may be a question posed that if we feel is important, even if it's been covered, we're going to ask that question to you, and maybe you can respond, somewhat briefly to it, or even point out the slide where you've covered that. And number three, some questions as you are presenting, come in on the same subject. Different people have essentially the same question. We will try to combine those questions, in the interest of time. So I'm going to kick off the questions, and whichever the three of you, John, Kit, and Rajesh, whichever you wants to respond, go right ahead. But let me just get right into them. We had a question. Are you aware of heat pump installations with natural refrigerants?
I can take that question, Scott. Thank you. Yes, so there are heat pumps with refrigerants such as ammonia and water. As an example, using reciprocating and screw heat pumps with ammonia as a refrigerant, where on one side you may be taking care of a hospital's cooling load, and on another side you may be delivering hot water to various buildings. In addition, there's a technology called absorption heat pump technology, which is driven by waste heat. It doesn't have compressors, and the refrigerant is water with zero global warming potential. So yes, heat pumps do exist with natural refrigerants, and waste heat recovery is a great decarbonization strategy.
Terrific. What is the range of CO2 emissions in metric tons that can be avoided per year through the use of these type of heat pumps?
Yeah, excellent question. It really depends on, what's the baseline, and are we talking about shifting away from coal and natural gas fired legacy systems? But if I were to, assume a very broad range, I would say the range would be, and again, it's very broad, it would be anywhere from, let's say, 2,000 metric tons of CO2 avoided per year to something like 10,000 metric tons of CO2 avoided per year. So 2 to 10,000, it could be a little bit smaller, it could be larger, but at least it gives you some range. And then it's not just the emissions that are avoided per year, but now multiply this by the carbon tax that Kit and John talked about, which is coming. It's already implemented in Canada, it's coming into the US, and it's going to be not only just implemented, but carbon tax will continue to go up. And so it's a significant carbon tax avoidance through the deployment of the water-to-water heat pumps that we talked about today. So I gave a long answer to a very simple question, but I would say 2 to 10,000 tons of CO2 per year is the number that I like to remember.
Okay, thank you. We had a question from someone, I believe, who works for a larger facility, and his question was, or at least for a large facility like his, wouldn't a large electric boiler increase carbon emissions at the source if his facility is in an area where it's mostly gas-fired electricity where he's based?
Yeah, I can take that question. So for sure, right? You need to understand how your power is being generated, right? And as I mentioned, in the presentation relative to coefficient of performance, right? Electric boilers are, right around 1 COP. And when you're talking about heat pumps, they can range from 3 up to 5 plus in terms of their coefficient of performance and efficiency. So they're more effective at moving energy and providing heat to the spaces. And so if you're using electric boiler, right, basically it's could be up to 4 or 5 times less efficient than, let's say, a heat pump chiller, or a water heat pump, I should say, in this instance. And definitely it's going to be based on, the grid, right, where the power is coming from. If you're using dirty, fuels in order to power the electricity, yeah, that could be even worse than using natural gas boilers, right? So all those things need to be considered for sure.
Thank you. We had someone submitted what I'll call a multi-part question. Let me just put it all out there in the interest of time. What particular York or JCI chiller models are used for heat pump applications? And then the follow-up question was what is the range of hot water and cold water temperatures that can be achieved and the maximum lift in Fahrenheit degrees?
Josh, you want to take that one?
Yeah. It's a very broad question, but I'll definitely follow to all those who submitted that question. And there's a really broad portfolio that we have that ranges from scroll to screw to centrifugal to absorption heat pumps. So it's kind of, I'm not trying to deflect the question, but what I would say is that in terms of temperature capabilities, we talked a lot about 170 F, 77 Celsius, but there have been instances in Europe where using a lower or ultra low GWP refrigerant such as R1234ZE, we have been able to deliver 185 F or 199 F. And in terms of heating capacities, it's anywhere from say 6,000 to 7,000 MBH or 6 to 7 million BTUs all the way up to say 38 million BTUs, in some cases even 75 million BTUs from one single equipment. So I know that I'm not answering the question succinctly because it's a very, very broad question. In terms of, it all depends. In certain cases, we may be limited to 120, 130 degrees Fahrenheit maximum hot water temperature that we can achieve from a heat pump. But from another design, we can achieve 170 and then much higher from another design platform. Also, the diversity of refrigerants plays an important role. So, so don't have a specific answer, but it really depends on a case-by-case basis.
Okay, as we come up on 2 p.m. Eastern, I want to remind the audience, we've got enough questions. We're going to go right up until our cap at 2:20 p.m. And again, if you have to drop off, the link that will be sent to you with the YouTube video will contain this Q&A portion, so it'll be worth checking out tomorrow. We had a question come in. Under what circumstances would Johnson Controls specify or recommend resistive electric hot water heating for a low temperature hot water system as opposed to a heat pump. And this gentleman mentioned in his case, he's talking about systems between 5 and 10 megs, maybe typical of a campus low temperature hot water district heating system.
Yeah, that's a tough one. I mean, there are a lot of factors involved. We'd have to know. I mean, I guess it would be a cost analysis to see if the first cost was driving the project, whether that would be advantageous. But it certainly would be you have to have enough first cost savings to go with an electric resistance heat system as opposed to a hot water heat pump system. So I think you'd probably have to evaluate it and understand what your payback tolerance was. But certainly from an energy standpoint, we can provide a relatively small water-to-water heat pump that would make the system much more efficient if it was hot water.
Yeah, and I'll add to that too. Is I mentioned this early on in the presentation as well. It's like there isn't a one-size-fits-all approach. There's not a line in the sand that we can draw saying, hey, this makes sense for heat pumps or this makes sense for electrical resistance, right? It really has to be dependent on the overall objectives of the project and the amount of capital that's available, right, and the length of time for that's required for the project in terms of completion, right, and what is the overall goals from a carbon emission standpoint as well, right? So there's a lot of questions, and I think that's part of the evaluation process, right? You kind of start high level and then you just kind of work your way in and funnel that down to get to more granular answers like that.
Thank you. Another question. What refrigerant is typically used to generate 170-degree temperatures?
So we have done 170F with 134A, or even it's possible with 513A. So it's not really, the refrigerant is not the limiting factor. So all the refrigerants that were listed on the slide, 134A, 513A, R1234Z, they can do 170F.
Okay. We had a question come in about how do these heat pumps meet the demands of certain institutions that require steam for cage washers, sterilizer, commercial dishwashers, and so on?
That's a very tough question, I have to say, because if you were to produce steam or low pressure steam for the things that you just mentioned, you need a higher temperature heat pump beyond the 170, 180, 190. And this kind of brings us into an interesting territory of industrial decarbonization. So if we are going to move away, let's say on a fossil fuel based steam heating systems, then you need heat pumps that can deliver much higher hot water temperatures to displace that steam. And this is something that the manufacturers are considering and are working on. There are definitely design challenges. Not to say it cannot be done. It has been done, including by Johnson Controls. We continue to make progress on this issue. But some of the, if the question is, can the CYK provide hotter temperatures equivalent to, let's say, saturated temperature of a steam? Currently, the answer is no, but things might change in future with different fluids and different designs. But it is an absolutely excellent question, very valid, and though the person who submitted the question probably meant it in a different context, but it is very important from even industrial decarbonization point of view.
Rajesh, if I could just add to that, I run into an awful lot of college campuses that are currently distributing steam, and they're converting with a heat exchanger to hot water at each building, right? So that's a situation where there still is a really good opportunity, because often you have a chill water loop that goes right by the building. So that's a heat source that's readily available. if you were to locate a smaller heat pump in the building itself, you can tap into that return chilled water, and that can be a heat source and provide your heating for the building. So there's still an opportunity in that case. And then I would also mention that I'm seeing an awful lot of colleges engage in a long-term project to convert their steam system over to hot water so that they can take advantage of heat pump technology on a more centralized basis. So what I would say there is if you are running into a situation where you're facing having to spend a lot of money to upgrade or repair your steam system, maybe start replacing it with hot water strategically, section by section of campus. Consider what buildings are needing simultaneous heating and cooling. Those would be great ones to put on that initial phase of your hot water loop that you install. So, there are situations where you need steam, but you can still take advantage of it at a building by building, on a building by building basis.
One of IDEA's young professionals has asked, will the phase out of refrigerant 134A at the end of 2023 impact your ability to generate higher hot water temperatures?
No, I mean, we already have refrigerant choices and diversity of refrigerants already mentioned on our slide, but it's a good question by our young professional. They are contributing so much to IDEA. Really appreciate the question. And actually, as we go from HFCs to low GWP and ultra low GWP refrigerants, it actually enhances the ability to get hot water temperatures. But excellent question. I really appreciate it.
Can all sizes of the York CYK heat pumps provide 170 Fahrenheit heating hot water? Or if not, is there a minimum size limit for a unit that can create 170 degree Fahrenheit heating hot water?
So as Kit mentioned, our existing buildings have the 180F, 180, 160F hot water loop. And so we need equipment that can do 170F. So far in the past, the York CYK was deployed for medium to large applications. And so we had the capability of delivering 170F. And so the time is now right to kind of look at the other CYK models on the lower end, also on the larger end. So it really depends. With different fluids, yes, we can get up to that 170F, but can each and every model do 170F? Probably not. Similar to any manufacturer, you have those, most of the time you have those sweet spots, and then there are some spots that are not sweet. So
exactly.
So the general answer would be 155, 160 on some other models, and then 170F on most models.
Okay. Does a ground source HX field need to be balanced in terms of heating and cooling on an annual basis?
I would say, I can take that question. I would say yes. I mean, you need to, to be honest with you, run a pretty in-depth energy simulation, to make sure that you're not rejecting too much heat into the well, where that you're not able to even leverage that as a source any longer because ground temperatures are getting too warm, right? So, that's where definitely doing a deeper dive energy analysis and making sure that, hey, have the ability to maybe reject heat to a cooling tower in certain times of the year, as an example, so that you're not oversaturating the earth with too much, heat, right? So that you're continuing to raise that temperature over time, for sure.
Okay. Two questions about the CYK that I'm going to combine. One was a question about, for the CYK, what's the minimum turn down ratio, for both the heating mode and the cooling mode? And also a question about the CYK, does Johnson Controls offer the option of a double bundle condenser on that?
Okay, so let's address the turn down first. So the turn down typically is, in the simultaneous cooling and heating mode, we need to be careful how we define turn down. Turn down is would say the general answer would be 40 to 50% of the design heating capacity. And which is about 30% or so of the cooling capacity. But generally speaking, most customers are interested in turn down with regard to how much can we go lower compared to the design value, which is about 40 to 50% is what my general answer would be. It really depends on where you're operating on the compressor map. Second is the question, I understand probably in our animation, the question was probably, the question came up about the additional bundle in the condenser. So what I would suggest is that, as I mentioned there were 3 animations that were shown: simultaneous cooling and heating mode. We're producing chill water and hot water for beneficial cooling and heating. In the heating only mode, we were not putting chill water in the evaporator. We're putting something other than chill water and still producing that hot water. The last mode was the cooling only mode, where the same unit needs to be operated as a chiller. And so in the cooling only mode, your hot water bundle is obviously not active in the condenser. You are circulating cooling tower water to produce that chill water. Having said that, we have heard from our customers that sometimes there are challenges when you are overproducing excess hot water. So how do you overcome that challenge? And right now, without taking customer names, I would say that some of our customers have found a solution to reject that excess heat to keep the system operational. So I have to follow up on this particular point. A lot of great questions have come our way. After the webinar is done, I will take a look at each of the questions and we'll try to incorporate in our part 2 webinar. Once again, I'm not trying to defer the question or deflect it, but just need to make sure I address all of those, John and Kit. And then, sometimes there are those elements that just deserves a little bit more internal deliberation before we put something out there before we are ready, So, but it's a good question. I don't have a direct answer to that one.
No problem. What is the largest unit in terms of heat delivery? Is it the 9.2 meg example? And what about the highest temperatures available?
9.2. 1 second, please. Okay, so the highest capacity is from a CYK is around 11 megawatts. And then if you go with the Titan OM, I believe it's around double that, 20 or 22 megawatts. So it's not 9, it's 11 and up to 22. So quite large.
Is the heat recovery chiller option a standard part of a heat pump?
So I can answer that, and John and Rajesh, feel free to comment on that. So
Yeah.
When I think about heat pumps are they're controlling to either to heating or they're controlled to either cooling, right? A heat recovery aspect of a piece of equipment is really just a byproduct of what cooling is being done at that time, right? So with any sort of heat recovering, it's controlling to cooling, and then you get a byproduct of hot water from that. It's not, heat recovery is not controlling to, let's say, the heating hot water or the heating side, of the loop. So inherently, in some instances, you can have water-to-water heat pump that can do have a water-to-water heat pump that can do heat recovery as its mode of operation. But heat pumps traditionally are controlling to either heating or to cooling, depending on that mode of operation.
We had 2 questions come in concerning the use of river water. One was, are there any ecological implications? as far as using river water as the evaporator? And number two, when you use river water for a heat source, does the water need to be processed before coming in contact with the heat pump?
So the answer to the second question is not necessarily, as long as it is just screened. It doesn't need to be treated. Similar to project we are doing in Canada, where it's not even river water, it is sewage wastewater. It is used directly, but it is screened. The first question about ecological, I'll have to get back to you specifically on that one, but the example that I gave from Europe was actually using river water from the city of Paris in France. What exactly what the compliance requirements, I'll have to get back. But I'll be more than happy to share not only just the ecological compliance aspect of it, but also what were the temperatures. I'm sure there are some limitations that you cannot go so high or so low. So,
is there an analysis of, as far as water savings, is there analysis of water savings from evaporation in a cooling tower, or is it really dependent on your location?
So it would be dependent on the location. Kit, I think in the model, we take that into account, do we not, in terms of how much evaporation is going to be present?
Yeah, there's three things to that equation, right? You've got for makeup water purposes, it's drift, right? It's blow down, and then it's evaporation. So all those things play into account in terms of determining how much makeup water is required in the cooling tower, to be able to, adequately make sure it's maintaining the right flow rates through the chiller, and all those things were taken into consideration when trying to, showcase any sort of water savings. But all that stuff is going to be really dependent on the location. I mean, if you have a drier environment like Phoenix, you're going to see more evaporation of water, let's say, versus New Orleans, where it's a very high mean coincident wet bulb, very, very humid type environment.
Is a good question. Is there some staged compressor approach that can be baked into a large HP selection? And what considerations are there to get maximum delta T and for redundancy?
sorry, can you repeat that question, please?
Sure. Is there some staged compressor approach that can be worked into a large HP selection? And maybe if so, what considerations do you give to get a maximum delta T?
I'll have to discuss this and get back to you.
Sure, sure.
Respond accurately to the question.
Sure thing. And can the hot water from the condenser be used for absorption chillers?
Sorry, repeat the question, please, again.
Sure. Can the hot water from the condenser be used for the absorption chiller?
Oh, I see. So absorption chillers are driven by hot water. That is commonly done. But they are limited by the entering hot water temperature. Typically, what I've seen is you need a minimum of 150 or 160 F hot water to drive an absorption chiller to produce chill water. So yes, it can be done. I mean, you can use the 170 F, but why would you do that, right? Because you're producing hot water for beneficial heating. But theoretically, yes, it can be done. If let's say industrial wastewater exists at those temperatures, by all means, an absorber can be used to produce cooling. Yeah.
We had, because we are starting to come up very near our max time, we had a couple questions come in about cost, life cycle cost, et cetera. And I'll just give one of those questions. Are there savings in terms of maintenance costs from the HP chiller versus a chiller boiler combination? And is there potentially life expectancy difference? And I think what some of these folks attendees are getting at is that if they are considering a switch to these types of systems that that you are mentioning, what should they be thinking about in terms of not just upfront costs, but really costs over the long term?
Yeah, so one of the things, right? I mean, the HP chiller is similar to centrifugal chiller. The compressor, the heat exchangers are standard components from a centrifugal chiller. Yes, there is that additional compressor, additional piping and complex controls compared to a chiller. But using a HP chiller that we just explained, everything is closed loop. You don't have those water treatment costs. The other thing is there is no combustion. So the maintenance costs associated with feed water treatment, boiler controls, boiler maintenance, boiler parts, all of that is eliminated. So I would say that this is something that again we'll cover in part 2. But overall, the life cycle cost of a heat pump chiller, particularly the cost of maintenance, service and parts, would be lower than a chiller and a boiler combo.
Thank you. And because we are now at 2:20 and have to start wrapping things up, there were a number of questions we did not have time to get to, including some that were specific to the latter portions of the presentation. And basically, we had some questions come in even during the Q&A that I definitely was not able to get to. All of those questions will be forwarded to the presenters. So be patient, and I'm sure they will get back to you. And my apologies that we did not have time to cover those today. Certainly, as we wrap up, I want to thank Kit and John and Rajesh for a terrific presentation. As they alluded to, this is basically part 1 of a 2-part series being presented by Johnson Controls. So the next one is going to be in November. And if I could ask whether it's Kit or John, whoever's controlling the slides, if we can move the slide to our upcoming events one, there it is. As mentioned, on Wednesday, November 9th at 1 p.m. Eastern will be part 2 of this series on large heat pumps, titled Large Heat Pumps, Carbon Reduction with Great Economics, Real World Applications and Case Studies. So if you've joined us for this presentation, we certainly invite you to join us for that part 2 of this Insights and Innovations webinar series. Coming up right this week, as far as other events at IDEA, this Thursday, also at 1 p.m. Eastern, we have a very special mini masterclass. It's presented by the IDEA Young Professionals Group. And they're going to be really pleased to be joined by Juan Ontiveros for a mini masterclass on district energy. While this presentation is, at least to some degree, geared to those with less than 10 years of experience in the district energy industry, we think, when it comes to Juan Ontiveros, we think that it is well worth anyone's time to hear his thoughts and what he did to really get the most out of the system at University of Texas at Austin. So whether you're new to district energy, it's a great opportunity to broaden your knowledge base. But even if you're a grizzled veteran, it's always great to hear what he has to say, not only about district energy, but also about organizational excellence and how to keep the trains running on time. And we still have certainly spots for that, because that is a delivered over the web. And I would be remiss not to again plug, in just a few months, we have coming up our Campus Energy 2023 conference in Grapevine, Texas at the Gaylord Texan Resort. That is going to be from February 22nd to February 27th to March 2nd, 2023. The registration is open. We've got the hotel blocks available, so we encourage you to go to that website, go to the specific link, or even to the IDEA website and register either in person or virtually for that event. It really should be terrific. And again, I want to thank Kit and John and Rajesh and everyone at Johnson Controls, for their presentation today. If you liked what you saw as far as these Insights and Innovations webinar series, we invite you to contact my colleague Tanya Kozel at tanya.idea@districtenergy.org, and she'll give you the full information on how you can take advantage of one of these opportunities. It is a great way for our manufacturers and service providers to connect with hundreds of potential customers and really show your stuff in that regard without any travel expenses. So again, from all of us at IDEA and for the 3 presenters from Johnson Controls, we want to wish you the best afternoon, and thank you for joining us.